Hello, I welcome you all in this course on power plant engineering. Today we will continue our discussions on hydro turbines. So, topics to be covered today are the radial flow impulse turbine, Francis turbine and Kaplan turbine. Now, we will start with the radial flow of radial flow impulse turbine. Radial flow turbines. Radial flow means the u keeps on changing, right? And u means the peripheral velocity of the wheel, it will keep on changing as we move from inside to outside or outside to inside. Now, the work output I have already explained, it is mass flow rate multiplied by VWU plus VW1 U1. It can be negative also. So, plus minus VW1 U1. VW is the will component at inlet and this is U1. Will component at outlet, this is peripheral velocity at inlet, this is peripheral velocity at outlet. And this is going to be equal to half mass flow rate V minus V1 square. This is the change in the kinetic energy, and this change in the kinetic energy has gone to the wheel for power generation. So, here we can easily find that VWU plus VW1 U1 is equal to V square minus V1 square divided by 2. M will be cancelled out, that is it. Now, VWU plus minus VW1 U1 is also change in the kinetic energy plus change in the kinetic energy of wheel plus change in the relative velocity, right. So, if we compare these two equations, we can easily find that u minus u1 square by 2 plus VR1 square minus VR square by 2 is equal to 0. Now, from here we can find the value of VR1 square by 2 is equal to VR square by 2 minus u minus u1 square by 2. If these two are equal, then VR1 is equal to VR. This happens when there is no radial flow, there is only tangential flow to the disc of the blades. Now, we will switch to some of reaction turbines, and Francis turbine is the most popular turbine in this case. So, let us first understand the Francis turbine. Francis turbine is a radial flow turbine, and in this turbine the fluid enters from the periphery of the disc. Suppose this is disc which rotates with a certain velocity, right, and it has vanes, it has an eye and it has vanes. So, fluid will enter from the periphery and will leave axially at the center. However, in the centrifugal pump, the fluid enters from the center and leave from the periphery. So, here fluid will be entering from the periphery and it will be leaving from the center. Now, we have to ensure that there is no shock entry or the fluid should simply glide over the vanes of the wheel, right. So, for this purpose there are certain guide vanes. It is surrounded by the guide vanes. There are certain guide vanes. The purpose of the guide vanes is to guide the jet of the fluid. So, guide vanes, they give direction to the jet of the fluid and they can move over a pivot. So, they can decide the angle of the inlet also, right. So, they are flexible, they are pivoted here and they can move, there is an angular moment on these vanes, and these vanes can guide the direction of the fluid which is entering the, which is striking the or which is gliding over the surface of the blade. Now, after this there are stay vanes also. Stay vanes are fixed and they are half in number of the guide vanes. So, if guide vanes are 20, stay vane will be 10. They are fixed, right, and these guide vanes are they also control the to certain extent the quantity of the fluid which is entering the blades, and stavings they are fixed, and the weight of the casing also comes on the stavings, right. Then there is a volute casing. Volute casing, as in the case of centrifugal compressor, there is a volute casing here, but from this side the fluid enters and it starts distributing here, right. As the quantity of the fluid increases or the volumetric of the fluid flow of the fluid reduces, because part of the fluid enters here, from here it enters the towards, or it moves towards this rotor of the turbine, right. So, the cross section area of the volute casing keeps on reducing, it keeps on reducing actually, this cross section area it keeps on reducing, so that constant velocity is maintained, right, and there is a uniform entry of the fluid from all directions. It is very important. It is very important for the design of the Francis turbine, for a good design of Francis turbine, that there is uniform velocity of the fluid is maintained throughout the casing, right. If we look from a different angle, the turbine will look like this. This is the volute casing, and after entering, after moving, over the blades, it will leave the turbine in radial direction. So, it is going to be like this, and below that normally a draft tube is provided. This is draft tube. The function of the draft tube we will discuss later on, right. The draft tube is provided to just to increase the output of the turbine or efficiency of the turbine, so that we can maintain lower pressure here, because here the pressure is atmospheric pressure. I will discuss draft tube in subsequent slides. Draft tube can be of different shapes. It can be a conical, cylindrical, or it can have shape like this. It can be an elbow shape also. It has to be not necessarily a cylindrical in cross section, or parabolic, or elliptical in cross section. It can be square also. It can be of a square cross section also. But draft tube is almost an integral part of a Francis turbine, because without draft tube a lot of energy will go wasted, right. Now, we will switch to the performance of Francis turbine. Now, as we have seen that when there is a radial flow of the fluid, the work output is mass flow rate VWU minus VW1U1. But here in Francis turbine, outlet is radial. When there is radial output, there is no whirl component. So, this is going to be 0. So, the output of the Francis turbine is mass flow rate VWU. Hydraulic efficiency, output divided by the energy available at the entry of the turbine. So, that is VWU by GH, because at the entry of the turbine M will be cancelled out. So, hydraulic efficiency of the this Francis turbine is going to be VWU divided by GH. Mechanical efficiency, there are different type of efficiency. Mechanical efficiency, this is actual power output divided by VWU. This power which is imparted to the impeller is not 100% converted into the actual power, mechanical power. So, there are certain losses in the bearing, losses due to friction, losses due to in the bearings, and the actual output divided by the power imparted to the wheel or power developed in the wheel. This ratio gives the mechanical efficiency. So, we can say the overall efficiency, if you take product of these two, then you will get P by GH. Actual power we are getting and actual power which is available. Now, in Francis turbine, as I said, there is a reaction turbine, pressure loss may take place in course of blades also. So, there is always a term which is known as degree of reaction for the design of the turbine. The degree of the reaction is going to be P by rho minus P by rho 1. So, P1 by rho 1 is equal to VWU minus VW1 by U1, and this is always 0. So, this is 0. So, VW multiplied by U. So, this is going to be the degree of reaction if you want to calculate degree of reaction of a Francis turbine. Now, there are certain properties of like Pelton wheel, there are certain properties of Francis turbine. Now, properties is the number n. N is, say, every wheel, I mean the impeller, it has certain width, right. So, it is width is b, and the ratio of b and diameter is known as n. And why it is important? It is important when we want to calculate the cross section area of the passage, because suppose this is a wheel, if you the side view of the wheel, right, and this is diameter d, so width, diameter d, width, and this will give the area which is available for the fluid flow. And if we multiply this with velocity of the flow, we can find the velocity q. So, q is equal to pi d b vf, right, or n pi d square vf. And velocity of flow we can always take from the velocity triangle, right. And further, there is a term psi. It is Vf by under root 2 gh, because initially we may not have the velocity triangle. So, but these are certain values. This is value of say psi has to be greater than 0.15 and 0.13, 0.30. So, it has to be between 0.15 from here, because h value is known to us. So, we can always find the value velocity of the flow. Similarly, peripheral velocity u by under root 2 gh. Now, the Ku value is 0.6 to 0.9. It is quite high. If you compare with the Pelton wheel, it is quite high. Anyway, the RPM of the this Francis turbine or specific speed of the Francis turbine is quite high in comparison if we compare it with the Pelton wheel. So, the speed ratio Ku is u by under root. So, this is how we will get the value of u. Once the value of u is with us, if n is with us, we can always find the value of d. So, out of these informations, we can find most of the dimensions of a Francis turbine. Now, if you want to design a turbine, then we can always say that the power developed by the turbine is overall efficiency multiplied by rho q gh mgh multiplied by the overall efficiency is the power developed by the turbine. Area available for the flow in a turbine, in the Francis turbine is pi d minus zt. Now, T is the thickness of, because on the wheel there are vanes, the thickness of the tip of the vane. In this area, there will not be any flow of water. If there are z number of vanes, so this much area will become ineffective. So, actual area will be available is pi dt multiplied by b, right, and a constant k. So, it can be k pi db if we are assuming T as 0, if we are neglecting it. And b, we always know that b is equal to nd, we have already discussed. Now, with this information, we can have the angles for the guide vanes also. Suppose we want to have guide vane angle. So, for the inlet of the Francis turbine, it is coming from the top, right. So, this is u, this is VR and this is V, right, and this is VF, right. Now, VF by W, VW, this is angle alpha, blade inlet angle, right. So, blade inlet angle or guide vane angle is same thing. Now, in order to find the guide vane angle, so guide vane angle which is alpha can be taken as tan alpha is equal to Vf by VW. That can be taken from the inlet triangle, because at inlet of the turbine, this is the vane, this is VR1, R1, and this is U, and this is V1, right? And this is V1 and this is alpha. So, guide vane will guide the jet in this direction, V1 direction. Wheel is moving with U direction, and this will impart the relative velocity VR1, VR in this direction, VR in this direction, right. So, this angle alpha, this is guide vane angle, can be calculated by Vf by W. An outlet, for example, at outlet, the angle phi, similarly, that angle phi can be calculated as Vf1 by U1, because outlet triangle is like this. It has no whirl component. Yes, so it is going to be like this. Outlet triangle is like this. It does not have any whirl component. So, the tan phi is going to be Vf1 by U1. Now, let us come to the draft tube. Draft tube, which I said is an integral, almost integral part of any Francis turbine. Now, what is draft tube theory? Let us assume that there is a Francis turbine and fluid is moving after radial movement, it is moving in this direction, and at the exit of the turbine there is a draft tube, right. Draft tube is also submerged in water, it is not left hanging, otherwise the atmospheric pressure will come here. So, it is submerged in water, let us say it is submerged in water at the height of h. Here the pressure is atmospheric pressure, right, and this h, this height is Z3, let us say this is Z3, this is datum, reference value. This as exit of the turbine is Z2 and inlet of the turbine is Z1, right. Now, we will do the energy balance, or we will apply the Bernoulli's theorem between 0.2 and 0.3. Okay. So, P2 by rho plus V2 square by 2 plus GZ 2 is equal to P3 by rho plus V3 square by 2 plus GZ3 plus GHF. Why I have taken GHF? Because there is always friction losses. When there is a movement of the fluid, in actual practice there are always friction losses. So, I have taken ZF into the friction losses into the account. Now, P3, if you look at the P3 by rho, this is 3, sorry, this is H, this is 3. No, this is not Z3, sorry, this is Z3, this is 0.3, exit of the draft tube, and 2 is the inlet of the draft tube, right. So, this is P3. So, P3 is going to be equal to, this is atmospheric pressure, PA by rho plus GH, pressure of this water column. So, we have taken 2 points in a draft tube, this is inlet of the draft tube which is 0.2 and exit of the draft tube at 0.3, right, and we have applied Bernoulli's theorem at 2 points, total energy here and total energy here, pressure at 3 is equal to pressure at this point plus pressure of the water column. Now, if we put the value of P3 by rho, PA by rho GH here, we will get P2 by rho is equal to PA by rho minus Z2 minus Z3 minus H minus V2 square minus V3 square divided by plus GHF. Just we have put this value of P3 by rho here and manipulated the equation, right. Now, P2 by rho is equal to PA by rho minus, now Z2 minus Z3, this elevation this minus elevation this is the length of the draft tube HS, difference in the elevation. So, HS, it is also called suction length. So, HS suction height plus V2 square minus V3 square by 2 plus GHF, right. Then this is HS, length of the draft tube which is above the water level, right. So, this is HS, this is HS, which is the length of the draft tube which is submerged in water is not taken into account. And this comes from this formula Z2 minus Z3 minus H, it is obvious. So, it is HS plus GHF, and this is going to be equal to PA by rho minus HS plus 1 minus K V2 square minus V3 square by 2. HF also we have taken as the change in the kinetic energy multiplied by K, because the friction losses in any flow in a pipe or any passage, they are taken as some constant their change in the kinetic energy or total kinetic energy multiplied by some constant. It is a normally diverging section. So, change in the kinetic energy multiplied by K can all comfortably taken as head loss due to friction, right. So, V2 is greater than V3 always, because this is a diverging section. So, velocity at 2 should always be greater than velocity at 3, and it means the pressure at 2 will always be less than atmospheric pressure. So, this will increase the pressure difference, and when there is a high pressure difference, more energy can be extracted from the fluid. Same thing happens in the steam turbines. In steam turbines, we have condensers. So, in the condensers, we are maintaining pressure of the order of 0.1 bar or 0.15 bar. The reason being, there are several reasons, and one of the reason is we can extract maximum energy from the fluid. So, here also if we are maintaining very low pressure at 2, we can extract maximum amount of energy from the flowing water. But the issue is, to what extent we can reduce the pressure at 2? We cannot make it absolutely vacuum. In that case, the water will start boiling. So, normally the head at state 2 is kept around 2.5 or 2.6, right. If you reduce the head at 2 or the pressure at 2 below it, in that case the boiling of water takes place. The temperature of the water becomes the saturation temperature of water, the boiling of water takes place, and when this water flows and this bubbles, when they collapse, it causes the cavitation. So, pressure is reduced to a certain extent that the vaporization of water does not take place or bubbles are not formed. Now, we will discuss the Kaplan turbine. Another reaction turbine is Kaplan turbine. Kaplan turbine is an axial turbine, right. So, there is only axial, there is sort of turbine blades are here, and there is an axial movement of the fluid. If you draw the velocity diagram of a Kaplan turbine, for the Kaplan turbine, it is going to be like this. This is VR1, this is U, and this is V1. And now here this is VR1, U, and this is V1. It is going to be like this. Blades are flexible, so inlet angles can be adjusted in the Kaplan turbine. It works on the head which is lower than the Francis turbine. So, if we put in a chronological order, so Kaplan turbine requires the minimum head, then it is Francis turbine, and then it is Pelton wheel. So, for this also it is N is equal to D by D, and Q volumetric flow rate is equal to pi by 4 D square minus D square velocity of the flow. So, velocity of the flow velocity in this direction, and this is the diameter of the hub. So, diameter of the turbine passage, and this is the diameter of the hub, and this much part is remaining through which the flow of the fluid takes place. It has casing. The Kaplan turbine has casing. It has 4 to 6 blades. Specific speed is quite high, and they are quite large in size. If you compare the size of the turbines in terms of power generation, suppose power generation is constant. So, smallest size will be for the Pelton wheel, then size will increase for the Francis turbine, and the larger, the highest size is going to be for the Kaplan turbine. There are tubular turbines also. There are several types of turbines. Now, tubular turbines, they do not have any casing, scroll casing is not there, and they have adjustable blades and both type of blades, adjustable blades and non-adjustable blades. Now, performance testing of turbines is very important. Performance testing. For the purpose of performance testing, there are certain dimensionless numbers which are to be considered. For example, number 1 is discharge number. It is Q by d cube n or Q by n d cube. This is known as discharge number. So, if there is a prototype and the model, right, if the model is same, has to perform same as the prototype, their discharge number should be equal. Number 2, head number. Head number is GH divided by n square d square. Third one is power number. Power number is P by rho GH n d cube. This is power number. Discharge number can also be written as mu by rho and d square. Mu by rho and d square. There is a dimensionless specific speed, ns, right. Dimensionless specific speed is n under root p divided by rho raised to power half gh raised to power 5 by 4. So, if you take the properties of water, right, and power you convert kilowatts to the watts, take the value of G 9.81, it becomes ns by 17.362. This is the dimensionless specific speed. Now, efficiency, because we have scaled down the dimensions, the fluid properties are not changed, right. So, efficiency of prototype and model may not match with each other. So, for that there is a formula 1 minus efficiency of prototype, 1 of efficiency of model is equal to prototype to power alpha Hm by Hp raised to power beta, right. So, this is the Moody formula where alpha is equal to 0.2. In the Moody formula, it is equal to dm by dp is equal to 0.2, right. For head is greater, when the head is greater than 150 meters, then mostly for the Pelton wheel or Francis turbine also, this formula can be used when the head is greater than 150 meters. That is all for today. Thank you very much.